Good morning, all. I welcome all participants for the 15th session on FDP on the sustainable solution in hybrid vehicles, sponsored by AICTE New Delhi, hosted by Department of Mechanical Engineering, Mite. On behalf of Mite fraternity, I welcome Dr. Ranga Srinivas Gunti, who is the advisory committee member and who has constantly supported us for organizing this FDP. I welcome you, sir.
Thank you.
I consider myself privileged to introduce the speaker, Dr. Ranga Srinivas Gundi, who has received his PhD from IISc Bangalore Center for Product Design and Manufacturing and done post-graduation from IIT Kharagpur. He is presently working as Deputy General Manager in Mahindra Research Valley. His research experience is over 20 years. He worked for various automotive and tractor industries. His research areas include computer-aided engineering in product design, data science in product design, multidisciplinary design optimization, automotive safety and impact engineering, IC engines, electric vehicles, and biomedical implants. He has published 42 research papers in international journals and conferences. He received more than 7 Best Performer Awards and 1 Patent Award for his contribution in the area of new product design and development. In his previous roles, he was responsible for developing various vehicle and powertrain systems and subsystems for automotive, farm, and marine applications. Presently, he is responsible for developing the frameworks, technical case studies on product development and process for technical capability building and technical assessments of Mahindra Research Valley engineering leaders. Teaches industry-specific case studies on data science and AI applied to mobility engineering at Virginia Tech India. Is active as a judge in various SAE competitions and a reviewer of manuscripts pertaining to international automotive conferences and journals. He is currently guiding few PhD and MSc research students in the area of automotive lightweighting and data science applied to product development. With this, I request Dr. Ranga Srinivas to take over the session. Over to you, sir.
A very warm welcome and good morning, ladies and gentlemen, professors, students. First of all, I would like to congratulate the entire team to have this initiative in place. And before starting my presentation, I would like to spend 5 to 7 minutes on why this is very relevant and how things are changing in the corporate world, especially in the mobility engineering. Am I audible to all?
Yes, sir. You are audible.
Okay, thank you. So 2 decades back, maybe in around 2000, most of the OEMs, Indian OEMs, started designing their own products from scratch. Of course, working with the various consultants and then with the Indian team, with the Indian engineers. And Scorpio is one such product, which was, from scratch. It was designed and manufactured and productionized in, indigenous in Indian support. All fine. So many OEMs came up with multiple products and started their R&D centers, right? And most of this, majority of this stuff are from India. Right? From 2010, there are some fundamental changes happened, not in the area of mobility engineering, but in the area of other technologies. Right? Some of the technologies you all will be knowing because Industry 4.0 is one of the buzzwords. So many of the technologies like IoT and cloud, data science and AI, user experience, AR, VR, additive manufacturing, computational power, a lot of computational power has improved very significantly. And all these emerging technologies, right? And customers are experiencing a different user experience through their advanced technologies. Maybe if you take an example of mobile phone, right? So one side, there is a domain, automotive engineering happening, right? This is a core domain. And the other side, from 2010, these technologies like 4G, 5G, communication networks, they improved drastically. So essentially what happened, the expectations of customers is changing, and there, we can only delight the customers when we integrate those emerging technologies and apply in the domain and solve our day-to-day engineering problems, mobility engineering problems. So essentially what it means is, you take an example of an X company, right? So there is a gap between what products we need to design and what competencies are required for an engineer to deliver that product, and the competency skill level of the engineers currently who are there. So there is a gap in the industry. So we continuously close the gap, bring the experts, and give a lot of advanced trainings to our practitioner engineers, expert engineers. We give a lot of trainings, right? That is one side. Now you imagine a setup in an academic setup. So definitely in an academic setup, most of the faculty, most of the students will be focusing on concepts, fundamental engineering concepts, right? And they have very good experimental facilities, right? Now, what is very important for academic right now is to fundamentally change their curriculum so that this gap between industry and academia can reduce. And once the engineer comes out of the college with slight training, maybe 1 or 2 months of training, he can be put on live projects and he will start delivering. To do this, I have a framework which I can suggest, that in all your curriculums, you have to capture 3 points. One is education, exposure, and experience, right? Education can be given through a degree program or any kind of certification program. And many of your students who are here, they can get access to many edX, Coursera courses in terms of domain technologies and emerging technologies. They can do audit for free, very, very advanced courses they can audit, and they can develop their skills. So it all comes under education. Right? When it comes to exposure, let's say this faculty development program, right? This itself is an exposure to many of you, right? Because in the last few days, you must have exposure to multiple speakers speaking about various challenges in this area of electric and hybrid electric vehicles, right? This is an exposure. And what we need to do is, we need to come up with more engagement with industries, do more FDP programs, and do a continuous engagement even after FDP on these topics. That is very essential. This FDP should not stop at this level. You should have continuous engagement. Right? And when you talk about the third E, experience, right? So you have to solve the real world society problems, right? You have to start interacting with the industries, startups, and then from third year itself, if it is a BTech or an MTech, or a PhD, you start interacting and start working with them, help them with your fundamental knowledge to solve real world engineering or whatever the problems, right? Society problems. And I would like to switch to my topic now. Before switching to my topic, there are 3 key things which you should capture in your curriculum or pedagogy. Your pedagogy should be highly multidisciplinary, right? Because most of the mechanical systems now are converting into electrical, electronic, software systems, right? We are talking about EV, hybrid electric. So an electrical engineer should understand the mechanical aspects, thermal aspects, and a mechanical engineer should understand the EMI, EMC, electromagnetic induction aspects. Otherwise, they cannot integrate various electronic systems into the mechanical systems, right? People should understand the safety aspects, chemistry aspects. So your curriculum should be highly multidisciplinary. And the second point, it should be highly applied, application oriented. And the third very important thing is data-based and physics-based. So data-based, because huge data is getting generated either through testing or through simulations, right? So data-based and physics-based, highly multidisciplinary, and application oriented. These are the 3 key things which should drive your syllabus or curriculum or your pedagogy. So with this background, I'm very glad that your college has come up with this thing. And I hope you have enjoyed all the previous lectures given by various speakers in this area. So my topic for today is can you see my screen, all of you?
Yes, sir.
Okay, great. So what I'll be talking about in the next 35-40 minutes is, You all know that, and today there are some challenges in coming up with the electric vehicle, right? In terms of cost, in terms of technology, right? In terms of range, and in terms of thermal issues. So you have gone through last few days, right? So what we'll cover here is how can I reduce the weight of a structural component, right? And which will essentially help in performance improvement in terms of range improvement. So we'll be using a technique called multidisciplinary design optimization, right? And which will help to reduce the weight of the overall structure, meeting various requirements coming from various other attributes, trade-offs, conflict management, right? So I will skip this slide because already you got exposed to this introduction. Okay, so we will be seeing why optimization, what is optimization and what is MDO, applications of MDO in automotive domain.
Sir,
Huh.
sorry to interrupt. Your screen is not visible actually.
Okay, so let me just, I had presented, let me just present once again. Can you see my screen now?
No, yeah, yes, sir. Now it is fine.
It's coming up?
Yes, sir.
Okay, thank you. So what we'll be seeing now is the lightweighting of automotive structures. So we will be seeing why is optimization required and what is MDO, applications of MDO, especially in mobility engineering, and what are the key challenges, why people don't use MDO, what are the specific challenges, and what are the benefits of MDO. Then we will see some specific use cases and how to reduce the weight of both IC engine powered vehicle and a battery powered vehicle. And we'll also see the advanced methods which are in MDO. Then we will see one very important tool at the end, how machine learning and AI can help in optimization, solving optimization problems in a very short time and with the required acceptable, practically acceptable accuracy. At the end, we will see if somebody wants to start their career in structural optimization using MDO, what should be their career progression? What all the things they should learn at different stages? Their learning map, I'll show you a learning map. So why optimization? So we all know that these are the three important metrics. One is we want improved design quality because customer pays for the improved design quality. What I mean by design quality here is the aesthetics, fit and finish, ergonomics, drive experience, perceived quality, all are design quality. Comfort, ride comfort, handling comfort, right? All are customer experience. So companies want to design products which are improved design. At the same time, meeting the regulatory requirements, right? Emission, whatever, safety regulations. The second important metric is we all work to meet three important things: time, cost, and performance. These are three critical metrics: time, cost, and performance. So optimization helps in improving design quality. It helps in meeting the project's time, cost, and performance requirements because we come up with an optimal solution meeting various constraints coming from design, manufacturing, sourcing, supply. And once we use this optimization tool, the engineer's time will get free up. Why it will get free up? Because the iteration, people will stop doing iterations, and then they will, most of the times the designs may be first time right, and you'll have time to do some innovative thinking in terms of patent search, coming up with various design concepts and making a quick prototypes, and then coming up with a lot of innovative frugal design. Right? So once you do optimization, right, use these algorithms, you tend to do first time right designs and you get a lot of time space to think and innovate. These are the three critical things. Why optimization? What is optimization? Very simple. Most of you must be exposed to this simple definition. You have an objective function. This objective function can be a minimization of weight or minimization. It can be multi-objective function. Right? In this case, which I'm showing, I can say the minimization of weight, right? F of x. X are design variables. Design variables can be shape, can be size, gauge thicknesses, can be material property, so on and so forth. Can be overall architectural parameters, so on and so forth. X is a vector. Constraints are those constraints, equality or inequality constraints, which are coming from your practical problem. If you see here on the right hand side, I have shown some of the constraints which will essentially translate to mathematical problem definition in the heading of constraints. So let's see a few of the constraints. Start with fluid dynamics, right? Durability, crash, NVH. So I would say for an electric vehicle, in order to give better performance, my coefficient of drag should be less than this. That's one constraint coming from EV platform, right? I cannot design my boxy structures like an IC powered vehicle. I have a strict target on the CD, coefficient of drag. And when you talk about durability, right, you have constraints on the thicknesses. Because if I have a weak, geometry or material, then I will land up in durability issues. The fatigue life may come down, and the customer have some warranty issues, right, with respect to failures. And when you talk about crash occupant safety, it's very important that the structures which we design are occupant safe and pedestrian safe, right? And for that, you need to design gauges in such a way that the gauges absorb energy and energy is not transferred to the occupant. And then you have NVH requirements coming from ride and handling, a lot of comfort requirements, vibration transmissibility, because you have multiple excitations coming from electric motor, IC engine, wind noise, tire noise, transmission noise, so on and so forth. So how do you deal with all these things? So all these constraints, NVH, durability, fluid dynamics, crash, architecture, multiple constraints in a practical problem will go as a mathematical equation in this problem. And then you have, of course, design variables, right? So design variables, if we talk about, we can have thicknesses, gauges, or any other, like geometry, or material property can be design variable. Okay. So now you all know how to formulate an optimization problem, right? And why we call this MDO? Because the constraints are coming from multiple disciplines, right? See, we must be seeing somebody working for 40 years in fluid dynamics as a CFD expert, right? Somebody working in durability expert for 35, 40 years. And somebody is a crash expert, somebody is NVH expert. And there are teams who work as specialized durability teams, fluid dynamics teams. So when you want to come up with a complete vehicle, right? System level vehicle, it is very important that these teams will talk with each other. They understand, they do some trade-offs, conflict resolution, and then they formulate the problem in a very systematic way, mathematical way, so that your optimized mass, is good for all the requirements. So MDO, because multiple disciplines are involved in the constraints. Okay. Now, so we know what is problem, we know what is MDO and why MDO is required, we know, right? And now let us look at it. What is optimization? Very simple, very layman can understand. Let's say there is a hill. If somebody asks what is a maxima point, then people will tell this is the maximum point, maxima. But if you put two fences, right, and then you give a constraint saying that a person should get inside these two fences, then find out the maxima. Then the point where the red flag is there, that's an optima. That means your optima will change, right, depending upon the constraints, right? Here constraints are fence. So what I'm trying to say is, in an automotive engineering problem, these fences are nothing but these constraint equations which are coming from various requirements, right? So this is a simple physical interpretation. Now, let us give 2 minutes on what are those trade-offs typically an automotive engineer should do whenever. So let's say you have a vehicle where a suspension is very stiff. Then what happens during turns? It is stable, because stiff suspension, it will not have a oscillation. Handling will be very good. But what happens if the suspension is very stiff? Your vibrations will be transferred to the occupant, right? And he will not feel comfortable because he will feel the vibrations, right? Both the floor and the seat. So how do you deal with the suspension? How do you design your damping systems, stiffness of the structure, so that your ride and handling both are taken care of? When you talk about HVAC, thermal comfort, so you must have seen talk given by Mr. Ravi Ranjan, right? A lot of challenges, thermal management challenges in EV. Here, what I'm trying to say is, when you maximize the comfort, right, then you may have to have penalty either in terms of the battery power or in terms of a fuel, right? So how do you deal with this? Then aerodynamics and crash worthiness. This is something which will excite. Many people will be thinking, why can't the cars can be completely aerodynamic and very stylish? Because this is A pillar, B pillar, and C pillar. If you see A pillar, can you see my cursor? All of you are able to see my cursor?
Yes, sir.
Great. So this is an A pillar. So if I reduce this acute angle, then the aerodynamics will be improved, very improved, and it will be stylish, right? But what happens when you reduce, when you improve the coefficient of drag, when you reduce this A-pillar angle with respect to the horizontal, when there is a rollover, it immediately crushes. It will not transfer the energy to the structure, and it will crush, and it will intrude, and it will damage there will be a severe head injury. So how do you make this A-pillar angle improved? Like, how do you balance coefficient of drag, the crash worthiness requirement, and of course, very important thing is occupant space between head and the surroundings. Occupant space is very important. You should have a very good occupant space. Then only you will feel very, your experience will be good in a car. Right? How do you deal with this? Then, if you see the structure, right, in this, if you see durability. So, if you want to improve durability, you will improve the thickness of the structure. Strength will improve, right? Material, you can use a high strength steel or very improved, steel which is having high yield strength and high failure strength. But then what happens if you use the steel with high strength? Then it may not crush. If the gauge is very high, if the thickness is very high, it may be rigid, and your energy, when there is a crash, the entire energy will be transferred to the occupant and not to the car, and that's a dangerous thing. When there is an accident, even the structure should crush. Considerable crush should happen in the vehicle so that the energy is not transferred to the occupant but to the structure. But at the same time, the intrusion should not be to the occupant compartment. So how do you deal with durability, crashworthiness? Then the trim design, right? So if you see the trim design, right? So A pillar, suppose there is an accident, somebody has not put the seat belt, is not there, right? And airbag is not applied. There is a chance that the head will impact the A pillar. Now, can I design some structures, structures which will absorb the energy in the A pillar? Right? Yeah, we can design, but what happens is the space is occupied, and you may not have this required occupant space. So you have to understand ergonomics, you have to understand safety, you have to understand multiple attributes. And the last trade-off example which I would like to give is on the piston bowl. If you see here, there are two lines. One is a solid line, deeper bowl, and another is a dotted line, right? The dotted line, the re-entrancy ratio is more. What it means is the air circulation will be better, mixing will be better in a dotted line because the circulation will be better. There is a re-entrancy ratio is high. In a solid line, the re-entrancy is less, right? The depth is more. So turbulence is less. It's okay. In one case, dotted line, your turbulence is more, which will improve the fuel economy. Right? Combustion will be good. In the other case, the solid line, your combustion, the turbulence is less. Right? But let's say somebody finalizes a dotted bowl because the fuel economy is good. Then what happens? You see the wall thickness available, wall thickness is less for dotted line. So even though it gives a better fuel economy, your durability may be in problem. So how do you balance? There may be thermal fatigue and your dotted line pistons may fail in the customer end, even though the fuel economy is better, 10% or whatever. So you have to balance. Okay. So now we understood what is optimization, why optimization, and what are the typical trade-offs in automotive engineering. And this list of trade-offs can go to more than 50, 60 in a typical automotive problem. What are the challenges in applying MDO? Key challenges in applying MDO, if you see, first of all, how to formulate the problem. It requires people from multiple domains. And then how to run various codes, Hypermesh, ANSYS, LSDAN, how to run, because it requires expertise, because each code is good in one phenomenon. Abacus is good in contact, LSDAN is good in crash, Adams is good in vehicle dynamics. So how do you find out experts in different softwares come together and start working on this? And then let's say you have the experts, you have the problem definition in place. Then at the end, when the results come, how do you interpret the results and ensure that your manufacturing cost, scalability aspects are taken care and your recommendations are going into the product? These are different levels of expertise is required. And once you get this expertise in place, then MDO should not be a challenge, right? So of course, the benefits of MDO already I explained, right? So quickly, I'll say MDO can manage complex problems. It can handle multidisciplinary problems. And then we need to come up with a single solver which can do a optimization, right? Because there are a lot of solvers doing multiple things. Can we come up with a single solver which will help to deal with all the disciplines, right? And then there will be a drastic reduction in computational time and cost if you get into MDO mode, right? Now, So now let us get into some specifics of EV and IC engine powered. Let's get into some specifics. So you all know, no need to mention, you all know why we are talking about EV. So obviously, if you reduce the weight of the structure, it will translate into either range improvement or fuel economy improvement. So I'll not stress on this slide. Okay. So now when you try to do light weighting, there are various ways one can do light weighting. One can focus on the material, one can focus on the joining techniques, one can downsize the engine, improve the efficiency and downsize the engine so that your overall weight of the engine will come down and your vehicle performance will improve. Or you can work on structure, doing the structural optimization like wall thickness, shape change, topometric, size optimization, right? Multiple options are there. In this example, I'll be talking about gauge optimization, thickness optimization. Now coming to a overall vehicle, what is the low hanging fruit? So this is a typical distribution of weight, right? Trims, seats and restraints, this is the weight. If you see, the majority of the weight is coming from body systems. This is majority of the weight is from body system. This is 34% is from BAW structure, either monocoque or body on frame. So present work deals with the body in white structure. So if you see the body in white structure, right? Next 2-3 minutes, I'll try to explain how to formulate an optimization problem in a passenger car. Okay. Again, there is an objective function, there are thicknesses, right? And there are constraints. And these constraints are coming from NVH, durability, and crash. Right? I don't want to get into details. I'm not sure whether we have time. Acha, anybody can tell how much time is left for me?
Sir, till 12:45, sir.
Okay, good. So let me just get into the details. So in this particular example, I took 3 thicknesses as the design variables, right? Thickness of the bumper beam, left rail, and shotgun. In a real world problem, the number of thicknesses will be huge, 40-50 thicknesses, which we'll be seeing in my next use case presentation. Right? So in this case, there are 3 thicknesses. And the constraints in a real world problem, you can have constraints more than 40-50 constraints coming from NVH, durability, crash, vehicle dynamics, ergonomics, and so forth, cost constraints. Here I am showing only 3 constraints for your understanding. One constant, natural frequency greater than 15 hertz, right? This may be an idle engine frequency. You don't want the structure to respond to an engine when you are in a traffic signal. No, when you are in idling condition, your idling RPM, the rotating imbalance should not excite your structure. So one can be that. Your damage fatigue life can be more than 1.2, right? There are structures like where the engine mounting structures, the rails, no, where hot spots are there. So your fatigue life should be greater than 1.2. Peak deceleration coming on the occupant should be less than 43 G. What it essentially means is that there are a lot of studies which say if your peak deceleration, chest deceleration is less than 43 G, then your injury levels are less. These are some of the constants. And if you see, there are 3 different models used for this. One is for NVH, one is for durability, and one is for crash. There are 3 different finite element models used. And your objective is to minimize the weight. Right. Now, quickly, I'll go through 4 different approaches, how the MDO is evolving. Right? The first, the very basic approach is RSM-based method, where you have a DOE, set of DOE done, and then you generate the DOE, you generate the responses, you develop transfer functions, and use those transfer functions in an optimization problem and solve the optimization problem. That is the response surface method. The second one, which myself and Professor Anindya Dev from IIC, we have developed a practical MDO, which results in a huge saving in terms of time to do the analysis, which I'll be explaining. And then there is something called hybrid MDO and then machine learning based MDO. Let us quickly see all these 4 methods. It is very difficult for me to communicate these details of these methods in a very short time, but I will try to do some justice on this. So we will start with an RSM method. RSM method, there is a response surface, there is an objective function, there is a response surface, and there is a feasible region. So what you are seeing a plane here is a constraint. If you see the fence, you have seen the fence in the previous slide, you have seen fence, 2 fences, they are constraints. So on a 3-dimensional, let's say, imagine this plane is a constraint. So if you say the feasible region is above this plane, then your optima will lie somewhere above this plane, your optima. At the same time, let's say your optima is minimizing, so you have somewhere optima below, right? So this is not your optimum solution of reduced weight, because you have a plane which is saying that your feasible region is only above this. So this will not be your optimum. There will be optimum somewhere mathematically somewhere here, right? This is typical response surface. And you can have a n-dimensional vector response surface. Here I am showing a three-dimensional. It can be an n-dimensional real world. Right? So what will be done in the RSM-based method? You have a DOE, you generate the responses, you build the transfer functions, and you plug that in your optimization problem, and then run the analysis, and you'll get a reduced mass solution. So here you got 15 kg, right? From 19 kg, you reduce it to 15 kg. Remember, this mass is only for these three components. In real world, you will have many number of components. Now, let me talk about the second one, which I'm talking about, practical MDO. So all of you now know RSM MDO. Now we are talking about a practical MDO. In practical MDO, what happens is you will try to reduce the number of runs which are required to do crash analysis. Why you try to do that? When you're solving an MDO problem, durability, NVH, vehicle dynamics, crash problem, NVH runs in a linear domain, so you will quickly get the result for whatever the DOE you have set. Durability, again, if you are within the yield limit, right? If you're, then again it's a elastic problem. Then again the time required is very less for solving durability verification plans. But the crash involves material nonlinearity, geometric nonlinearity, right? And then contact nonlinearity. So what happens when these three nonlinearities are there, and the number of components vehicle level you're trying to solve, each run will take huge, many number of days, right? So what was thought? So along with my professor Aninja Dev, what we thought is, why can't we design a method which will reduce the number of crash analyses, so that you will get a substantial improvement in the reduction in time, at the same time meeting the accuracy. So here you see, here you go. First, to do NVH, apply NVH constraints, right? So you just chalk out those which are meeting NVH constraints in the order of minimum mass. Then you run the durability runs, and then whichever are meeting the factor of safety requirements, you sort out in order of minimum mass. Then you start doing crash analysis from the point where it meets both NVH and durability. So essentially, what happened in this method is, earlier you had to do 107 crash runs. Now you will do only 7 crash runs, and you got the optimum solution. So what it means, you got an optimum solution. You got reduction in mass in a practical MDO, 19 kg to 16 kg, right? And if you see the time taken, in an RSM-based method, it takes 62 hours to solve the problem. And in a practical MDO, it takes 14 hours to solve the problem. Now, this, you can imagine, this method can be applied at vehicle level. And what was applied here is a vehicle level only, but the design variables are only 3, shotgun, rail, and all. The same method which is applied in the vehicle, we can include many design variables, and this time reduction will be a constant. It's 1/4 computational time. Same accuracy at 1/4 of the computational time. So 4 days, reduce it to 1 day. Now quickly I'll go through the next method, hybrid MDO. Hybrid MDO is a combination of practical MDO and equivalent static load method, where one of my student, Mr. Sairam Peddi, who is doing PhD in IIT Madras, he is driving this equivalent static load method in combination with what we have done in practical MDO. So what it means is, in a hybrid MDO, even the nonlinear crash runs, right? You can convert a nonlinear domain to a linear domain, do the optimization in linear domain, and then gain the time required. So I know it is very difficult for all of you to, in the short time, to realize, I cannot do justice to this method. What you can pick on this pointer, and you can get into details when you get time. So hybrid MDO is a combination of practical MDO and equivalent static load method. Equivalent static load method is converting a nonlinear domain problem to a linear problem, do the optimization using Genesis algorithm, and then come back to your map back to your original problem. This gave 1/8 computational time reduction. It's a huge benefit. And now what I'm talking about, a very important aspect, is machine learning based MDO, which all of you will surprise why AI, data science, and all these advanced machine learning based methods should be in the curriculum for automotive mechanical engineers, right? How this is relevant. So you will just realize after this example. So let me quickly go to machine learning based MDO. So when I'm talking about machine learning based MDO, I changed the problem definition slightly. Problem definition structure is same what we discussed in the previous optimization problem. Here we are talking about again minimization of mass, but the number of thicknesses are more here, which we'll see in the next slides. So it's a practical problem where more than 30-40 design variables are there, which we will see in the next slide. And the constraints what we took here is intrusion, because this is coming from regulation, 40% IHS offset, less than 82 in some intrusions. And natural frequency of one of the component, which I have not mentioned what is that component, natural frequency should be less than or greater than so and so, greater than some value. The value is not given here. Natural frequency greater than some. And this constraint which you are seeing here will be different for an IC engine vehicle and an electric vehicle. So how do you find out these constraints? Typically, first one is coming from regulation. Third one is coming from durability, maximum stress. Second one is an NVH constraint, which is coming from where it is coming. So typically what we do a lot of experiments to come up with these constraints, right? We do a lot of experiments. So, so this is an optimization problem, minimization of mass. Many gauges are involved in this, and there are some constraints related to regulation and NVH. And NVH, when you talk about, now I'll talk about an electric vehicle. Suppose if you want to finalize a constraint for electric vehicle, how do you do this? This will be something interesting and relevant to this electric vehicle platforms. So what I have done is I took two vehicles. One vehicle is an IC engine powered, and the same platform, just the IC engine is replaced with the electric powertrain. So the structure is same, slight modification in the package to accommodate the powertrains, right? Prepared two vehicles and kept microphones and accelerometers at three different locations. One microphone on the engine or powertrain. See, this is a motor, right? One microphone near the motor and one microphone near the IC engine. Right? You can see the microphone here. It is glued here. You can see microphone. And of course, the accelerometers are there. One microphone near the co-driver and one on the rear seat, and some accelerometers on the floor. So what was done is two vehicles, right, are instrumented and run at different speeds, 20 kilometers per hour, 30 kilometers per hour, 60, 80, whatever. And then a graph, noise versus frequency, is taken. The item marked green is the electric vehicle version, and the item marked, if you see the histogram, the color blue is the IC engine powered. So obviously the noise levels are more in IC engine powered. And there is a significant reduction in the noise levels in the electric vehicle version, right? I'm talking about the gross noise. So we've done the experiments at different speeds, then got the FFT, and we see some resonances at motor switching frequency, controller switching frequency, and many resonance points within the 0 to 500 hertz because of various excitations coming from togging. There is so motor excitations, rotating imbalance on the motor, cogging torque frequencies, and multiple road excitations, wind noise excitations. So all these things will lead to the resonance modes. So what I'm trying to say here is that if you see the right hand side picture, since the noise levels are less in an electric vehicle version, can we increase the noise levels? Because customer is okay, because the IC engine powered vehicle is selling with that kind of noise levels. Why can't I increase the noise levels? It essentially means, can I reduce the stiffness of the structure, right? Increasing the noise levels means, essentially it also means that can you reduce the stiffness of the structure? And when you try to reduce the stiffness of the structure, the gauges can be modified, and it may result in the reduction in the mass, overall mass. And this reduction in the mass will help in improving the range. Now, how much you should reduce stiffness? So those insights will come when you really do experiments on actual vehicles and come up with this kind of plots and see what is the gap at different frequencies and what is this 80 hertz, which is that excitation, how much potential I have at this. Can I reduce the stiffness in this frequency zone? And this will result in the improved mass optimization, right? And at a higher frequencies, what is very important is by structural changes we can't do. We have to do many other ways of masking the noises. You have to design sound packaging at higher frequencies. That's a different method altogether. It doesn't come on structural lightweighting at higher frequencies. But at lower frequencies, you have potential to work on stiffness of the structure fundamentally. Okay. Now, you saw the problem definition and you saw how one constant is coming from experiments. Because here, once again, I'm coming back to the slide, we ensured that this second constant is coming from those experiments, the experiments which were done on the real vehicles, right? Like that, you have to do many experiments and build many constraints, right? Now, you have a problem definition, you have done some experiments, you have finalized the constraints, and your gauge, your design variables are the thicknesses, right? Now start doing the DOE, design of experiments. So around 200 data points, right? 200 data points, 48 thicknesses, and you got NVH responses, response 1, response 2, response up to response 15. These are the model frequencies at various various locations of the components. These are NVH responses. Second table you are seeing right hand side top is a crash response. You have 14 design variables and 9 responses. These responses are the intrusions at different locations. You can ask me, in NVH you have 48 design variables, why in crash there are only 14 design variables? Because when you talk about IA offset impact, frontal impact, the main constituents are the front end structure which will absorb the energy, and the rear structure will be essentially as a rigid body. So your number of design variables can be tackled, 14 responses. Now in the durability, if you see, you have 26 design variables and then you have responses. These responses are the maximum stresses at different locations of the vehicle, right? Okay. So you have a new platform, you got the build, you have done the CAE, and you got this 200 data points. Can one develop models, machine learning based models for these responses? And these machine learning based models, once they are developed, they can be used when you are trying to come up with an improved design or scaling that platform. So when you are actually doing a new platform upgradation, these machine learning models, which are developed with these data sets, can be used at the concept stage of the product development. So let us see how these machine learning models, okay. So what was done is, first feature, these are the features which are common to all the 3 attributes, NVH, durability, and crash. You can see these are the firewall, floor, and some of the structures which are critical to all 3, right? And these are the machine learning models for footrest intrusion, for model frequency, and for stress analysis. And if you see the predicted versus accurate, the accuracy is good, right? Now what we can do is, using these 3 equations, these are machine learning based equations, 1, 2, 3 equations. Where these 3 equations will go? Again, I'm going back to this slide. These are the 3 constraints, and the first constraint, intrusion, is that equation which I have shown you, and that equation is coming from the when applying the machine learning models on the DOEs at 200 design points, right? So we have responses for all 3, NVH, crash, durability. We got the responses and we developed the machine learning models, and these machine learning models are used in an optimization problem, and you can apply any optimization algorithm, either gradient based optimization algorithm, and then try to come up with the optimum thickness meeting all the 3 constraints, right? Here you can see there is a 20% reduction in the mass of the structure, and more than 20% weight saving was realized for an EV platform, because in an EV platform there is a potential to reduce the stiffness of the structure because there is a gap in terms of the noise levels, right? And all of you should understand one thing. What I'm trying to say is, dealing NVH for EV is more complex than NVH for IC engine, because what happens, there are certain noises which are coming from tire, which are coming from wind, which are coming from wiring harness rattling inside the mountings, inside the clips, buzz, squeak, rattle, because of fit and finish issues. They will become dominant. Your hydraulic power steering, hydraulic flow, and intake. So what happens is, these noises are masked in an IC engine vehicle, right? But now these noises will come up very significantly in an EV powered vehicle. So how do you deal with these noises, right? This is very critical. So NVH is you have to deal with in a different way in which, so there is no engine which is masking these noises, and you have to take care of this. But what was shown here is a BW structure, how the stiffness can be reduced, and how can you use machine learning models to reduce the weight of the structure, right? And the last one or two slides, I will mention on the powerful ML based techniques which recently I have used on one of our problem. I cannot do justice in this short next 10 minutes on this topic, but one thing I can give you. You saw this slide previously. There are 200 data points and 14 design variables for crash analysis. When you apply forward feature selection and clustering, these are the machine learning based algorithms. Forward feature selection and clustering. When you use these algorithms, what happens is the number of data points will reduce to 5 data points, and design variables can reduce to 3 design variables. At the same time, getting the same accuracy. You can see here, the original DOE has 200 data points, and it took 133 days to run this analysis. And using dimensionality and volume reduction, you can just use 5 data points, and you can get the same accuracy. So the accuracy of this particular model with 5 runs and 3.3 days is to 85% accuracy we have. So what I'm trying to say here is, I want to once again repeat this statement. We have the original data set. On the original data set, I applied forward feature selection and clustering algorithm. Clustering is applied on the rows. And because of this clustering applied on the rows, number of rows came down from 200 to 5. And the forward feature selection is applied on the columns, and 14 columns are reduced to 3 columns. What it essentially means is, somebody do the analysis using this big database, somebody doing the analysis with this sheet of data, you will get the same prediction accuracy, more or less. But the time required to run this DOE is very less, because the number of runs required is very less. And especially this is very useful for analysis involving CFD, right? Because CFD will take a lot of time. Crash will take a lot of time. Highly nonlinear analysis, you can use this technique of forward feature selection and clustering to reduce the original DOE, right? So this is one takeoff. So what it essentially means is, an automotive or a mechanical engineer should deep dive into these advanced mathematical concepts, linear algebra, machine learning, right? AI, and then start applying to solve their problems, day-to-day problems, in terms of what are the product you are designing or what are the process you are designing. You should keep applying these things. So this is my last slide. If somebody wants to have a career in MDO, a beginner should have basics of mathematics, mechanics, strength of materials, finite element method, computer programming, basics of CA optimization. So most of these are covered in your curriculum. A practitioner, let's say at third year of your engineering, you can start working with some few engineers who are actually working on these problems in an industry, and start gaining these skills, right? Typically, practitioner is those who has some 3 years experience in an industry. He joined after BTech or MTech, and then 3 years experience, he become practitioner. And these are the skills. You should know CFD, you should know vehicle dynamics, crash, NVH, and advanced finite element analysis, right? And an advanced practitioner should be in a position to use the emerging technologies and apply on this and try to come up with the frugal methods. And an expert, especially, what he should do is, he should come up with various ways of MDO automation. How can you use Python and interface all these softwares together, right? LS-DYNA, Crash. Can I come up with a own product, MDO product, right? That kind of thinking and that kind of vision an expert should have. And you should use a lot of advanced concepts of innovation, right? And then biomimicry, and integrate with this MDO, and then solve the problems. And this MDO can be applied to many domains, right? Which today I have shown you the lightweighting, one aspect of this. It can be applied to aerospace, medical, biomedical, agriculture, and many others which I have not mentioned here. So I think with this, I will thank everyone for listening. And then that's all from my side. Any questions? I'm open to take some questions.
Participants, Can enable your mic? Pose your questions. So I have a query on that regarding consideration of variables. Sir, for RSM, the input variables are very important. Sir, how, like, if you're considering the variables, there will be n number of variables. How to sort that variable, like, how to consider the important variables that will be affecting the system?
Very good question. So excellent. So what we need to do is, let's say a domain expert in let's say 25 years domain expert, right? So if he sees the spreadsheet, he will immediately come out of this 100 variables. These are the 10 variables which will affect, right? A domain expert. Let's say somebody is not 10 or 15, 20 years. There are some methods in machine learning. Okay, what, like heat maps? Heat maps. You can note down heat maps, which will give the correlation between various parameters. Let us say an example, you want to know the fuel economy, right? And what are the parameters which are affecting the fuel economy, right? You want to know. What you can do is, you can see the data, vehicle level data, and then if you use heat maps and decision trees, right, it will say you, okay, if you are running in third gear for most of the time in city drive, the fuel economy is getting affected at a vehicle level. If this is the operating range of your temperature profile, and this is where when the NOx is becoming better, there is a problem with fuel economy. So what happens is, heat maps, decision trees will get you those 4 or 5 variables which are very critical. And the second point, if you see my slide, can you see my screen?
Yes, sir.
Okay, so there is something called forward feature selection. You can note down. So this will help you see, out of 14 design variables, how many design variables it picked?
3.
3. And this is coming from that forward feature selection algorithm. So these are the 3 variables which are very critical for that response. So there are various algorithms, mathematical algorithms, which will help you to bring from 100 to 10 and 10 to 5.
Thank you, sir. Sir, one more query. It was really interesting regarding that learning map. Sir, as a student, so what are the skill set that you focus that a student should acquire in order to be an MDO specialist for a student, sir, in terms of student's perspective?
Okay, so first is you must have gone through rigorous mathematics in your first year, right? You should be very strong in mathematics, linear algebra. You should be very strong in mechanics if you are a mechanical engineer. And not only mechanics, suppose this MDO is also applied to electrical electronics, because there are EMI, EMC. So you should have, essentially, you should be good at your subjects, right? Whichever subject you are taking. And then start using some tools, advanced tools, which are available in the market, right? Like various simulation tools which are there to solve specific problems, right? And then once you get into that, and then start building your own problems after discussing with the practicing engineers who are working in various industries, then work on one internship project. And then once you work on that internship project, you will get the confidence that you can add value to the, to the practicing engineers or to the product. And that is how you can pick one by one, and you can start solving many problems in this space. So I would say you should be very strong in mathematics, your fundamental domain subjects. Then you should be good in tools and techniques and softwares which are available to solve various problems, electrical, electronics, mechanical problems. And then you should work on real world problems, which are often defined by the practicing engineers. This is how you should get into.
Thank you, sir. Sir, no more query. With this, we have come to end of this session. I sincerely thank Dr. Ranga Srinivas for an informative session on lightweighting of EV using MDO. Highly multidisciplinary, highly applied, data-based, and physics-based are the key guidelines to the students from Dr. Ranga Srinivas. And the topics like problem, like formulation of problem in passenger vehicle, key challenges in applying MDO, and especially that learning map to all participants as well as students was an eye-opening. On behalf of Mite fraternity, I thank Dr. Ranga Srinivas for his valuable time and also for supporting and guiding us for organizing this FDP. So I thank you, sir.
Yeah, thanks a lot, and my special and sincere thanks to Dr. CRR, because he's the very reason why I got into this is because I know him from my old days. So because of my relationship with Dr. CRR, I could get into this and started supporting him. And thanks each and everyone, faculty, students. Thanks a lot.
Thank you, sir.
Okay.
Uh,
Can I quit?
yes, sir. Yes, sir.
Thank you. Thank you.
Now I welcome our beloved HOD to take care of the session regarding the valedictory. So I welcome you, sir.
Aveen, am I audible to you?
Yes, sir. You are audible.
1 minute. Just a minute. Okay. Good afternoon, dear participants. We have come to the end of this faculty development program on sustainable solutions in hybrid vehicles, which was sponsored by AICTE New Delhi and was organized by Mangalore Institute of Technology and Engineering. This particular program gave us a platform through which we could exchange our knowledge and improve our ability in hybrid vehicles in various engineering applications. I would like to thank all the participants for their active participation throughout the faculty development program. There were totally 15 sessions spread across 5 days, starting from 14 December till today. I'm happy by which the things have gone throughout the sessions. There were numerous provisions for the exchange of knowledge, which was utilized at a full pledge by all the participants and our students, and even the speakers of this faculty development program. I wish all the participants a great success in their future happenings and hope that this program and sustainable hybrid vehicle technology would help them in their research activities and academic activities. I also wish the participants use knowledge gained in this program in enhancing the skills of hybrid vehicle technology. Once again, I thank you for your participation. Also, I wish to thank all the eminent speakers who gave the time for this program and shared their incredible knowledge with all the participants of the program. And even I thank AICTE for having sponsoring this program to conduct in better way. I thank our management, in particular our Honorable Chairman, Mr. Rajesh Chevta, and Principal Dr. G R Prasad for their great support in organizing this event. I would like to thank Mr. Swaroop, the co-coordinator of the program, and session coordinators of the program who organized the things seamlessly and flawlessly throughout 15 sessions.
Quiz timing, sir.
My dear participants, today, as per the AICTE norms, there will be a small test on this program. What are the things you learned? The test duration is about 3 hours. The session link, test session link will open at 2 o'clock and it closes exactly at 5 o'clock. Please think you have sufficient time. during the previous session, what had happened, previous FDP, what had happened, we posted the question at 2 o'clock. Immediately at 2:15, the participants gave, one or two participants gave the result immediately. I mean to say, they submitted their results and the answers. They failed in that. You all know that as per AICT norms, you need to score minimum 60% of the total marks. The test will be for 30 marks. You need to score 18 marks. Please take your own time. You can discuss among you, or you can Google the things. Then you post your question, your answers for this. No need to be hurry. You have sufficient time. So at 2 o'clock exactly, the session link opens, and only one submission we are going to accept. Don't go for multiple submissions. Please think and submit. Those who get 60% minimum marks, for them only the certificate, e-certificate will be issued. So today is Friday. By Monday or 2 days, the certificate will be issued. It will come to your registered mail ID. Okay. And session link, the test session link also will come to your registered mail ID only. Okay. And one more thing I want to highlight, for all these 50-day sessions, we have recorded the sessions and it will be uploaded in the YouTube. Those YouTube links will be shared to you in your in the registered email ID only. If you have any clarification, you can discuss with me. Thank you one and all. All the best.